Okay, good afternoon. Let's start lecture. Okay. So Dr. Lucas and I are working really hard and marking the midterm exam and then a couple of TAs. Hopefully we could finish this week. Okay, and give it back to you next week. But in terms of the initial impression when I was marking exam, not about grades, but really it's about the proper writing that you should actually stick to. You know, it's during when you're doing assignments or doing questions. So one of the things I keep mentioning, when you solve an integral, for example, 0 to 3 x squared, okay? So many people just stop there, right? That's the integral. That's not an integral, right? You need to write this down. That's a full integral, isn't it, right? Yeah. So many examples like this that you should actually try to avoid in the regular times, okay? Not to avoid that from happening in the exam. Anyway, okay. We'll talk about a new topic now. In previous lecture, basically we talked about is given a function f. Okay. It could be a function 2 variable, a function of 3 variable. Okay. And then we have this so-called the gradient. The gradient of f, okay, is written as this. Okay, that's basically what we talked about in the previous lecture, the gradient vector. And I mentioned about the physical meaning gradient vector is it's first of all, this is a direction, right? It's a vector, and the gradient vector basically gives you the direction for the greatest increase for the function f at here. Okay, so basically it's a direction for the greatest increase in f. Okay, so now today we're going to talk a new topic, which is called directional derivative. It's a directional derivative. First of all, if you neglect this adjective words directional, basically it's a derivative, right? Okay, so essentially what we're going to talk about is a derivative. But it's a little bit special. It's a so-called directional derivative. It has something to do with the direction. So I'll start with a very simple concept here to show you what really direction really means here. Okay, so let's say consider a very simple case. Function of 2 variables. So when you learn for function 2 variables, I'm going to give you basically 2 cases. Yeah. This is very unconventional. So if the first case, let's say, ask you to take the derivative or to calculate the slope. Okay. And this is the definition you learned. Okay, so this is definition calculate slope here, right? So let's say I'll illustrate based on this definition and here, what does that mean basically? Okay. Let's say, for example, if I give you a specific function y equal to x squared, so you calculate the slope, which is basically 2x. Okay. Yeah. Now, if you plot this curve out, that's basically it's a curve. Okay. Like this, right? It's a parabola curve. Okay. Yeah. So if I look at this definition of derivative here, basically what it's saying is you increase the x by Anyway, you increase the x by delta x at here. Okay, so let's say if this is x at here, you increase the x by a small quantity, positive here, delta x. So that basically x plus delta x here now, and then you calculate the slope. Okay, the different color here. So this is essentially green color. So at this point, you draw a line in here. So you calculate the slope basically, right? Okay. So that's df over dx like this. Okay. Yeah. So let's see if I give you a specific number at x equal to 1, we get our slope equal to 2. Okay. So the slope basically says if you increase right to the x by small quantity, I don't know how much, maybe 0.1, then there will be basically an increase of function f value, and the rate of change for the function f is given by the slope k equal to 2 at here. So apparently you can see it's going up, right? Okay, because this is greater than 0, so the change of function f will go up. Okay, right? Now in this case here, what I want you to establish here, so this is basically from x to x plus delta x. Okay. Now more specifically here is you are essentially now you are going in the positive x-axis direction, okay, by a delta x change. Okay, yeah. So that's the conventional derivative. How you can interpret that? You increase the x by a little bit, the positive delta x in the positive x-axis direction, right? Okay. Now let's take a look at the second case study here. Okay. Okay. Now this case, I'll consider the same function, for example. Okay. Now this time I'm gonna calculate my slope actually slightly differently. Okay. So I'm gonna calculate like this. See the difference now? Right. So now the difference is what? Instead of f of x plus delta x minus f of x, I'm going to use f of x minus delta x minus f of x. Okay, and then over delta x, so let delta x go to 0. See the difference, right? So the difference basically, previously you're going to increase the x by a positive delta x. Now this time we're going to reduce the x by a small quantity delta x set here. That makes sense? Okay. So that's the difference set here. Now, if I use this formula right here, okay, if I use this formula and then apply the function y equal to x squared, and let's calculate this thing here. Let's see what do we get for the slope. F of x minus delta x can be simplified into negative 2x delta x, and then fx here, actually sorry, the whole thing can be simplified into this. Okay, so this minus this can be simplified into this and divided by delta x. Okay, so this whole thing will be equal to negative 2x. Okay, so negative 2x. So if I calculate the slope this way, I'll get, instead of a positive 2x at the previous case, I'll get a negative 2x in this case right here. Okay, so the slope is different now, right? Slope is different. So in this case, basically, let's see if at x equal to 1, then the k2 will be negative 2, right? So it's less than 0 at here. Okay, so less than 0. So let's say, for example, okay, if x equal to x goes from 1 to 0.99. So that's the idea, right? So initially at 1, but then it goes to 0.99. Okay, so your delta x is basically negative 0.01. Okay, so you have a negative increase. Okay, so essentially if I draw it here, okay, if I draw it here, this is your x here. Here's a 1. So it goes down from 1 to, let's say, 0.99 like this. Okay, so it goes this time it goes this way here, right? Instead of the other when it goes that way. Okay? But if you think about it, basically, when you go from here to here, that slope, if you look at the drawing, it's the same thing, right? It's the same thing here. But in this second case here, what it really happens is your slope is negative. Basically means if you go from here to here, the change for the function is actually reducing. It's decreasing, right? It's decreasing here. Okay. So it's a little bit actually confusing in here, but the idea is what I'm trying to show you here is we're going to actually try to get away from the conventional slope concept. We're trying to stick to a concept for the slope which is related to the direction of change. Okay, direction of the change now. So, for example, okay, I'll use a different color here to do a little bit drawing in it here. Okay, yeah. Let's see if I can do this successfully. So I'll draw the XY axis at here. Now this time I'm going to draw the okay. So this is the y equal to x squared curve. So I'm drawing it in a red and a green color. Okay, two different colors at here. Okay, yeah. Okay, so for the first case, for case 1, what's the direction of a change? It's this. This is the direction of a change here, right? So I'm going to use a positive s as indication of the change at here. Okay, yeah. And when we draw the slope or when we draw the tangent lines, okay, so basically you have to stick to a certain coordinate forming convention, and it's always the right rule. Okay, so always the right hand rule. So in this case here, if I want to draw, just like basically you're gonna have to look at it from this direction. So look at this direction, from this direction in here, then you have the convention of basically x and y at here, and this is your red, and this is the green. Okay, like this, right? Red, this is green. So in this case, this is x, and the same thing. I'm going to label this as a positive s at here, right? So that this time the positive direction of going coincide with the positive x-axis. That make sense? Right. So now you can draw maybe some sort of a slope lines at here. Okay, you can draw some sort of slope lines like this. So this clearly indicates if you have a change in the positive s direction, then you have a positive basically slope change, right? Positive slope. Okay. Yeah. Now, what happens if I go the other way around, right? So let's see here now. Basically, now this drawing here will be like this now. It's basically the same curve. Okay, the same curve right here. So this is y, this is x. But this time you are going to that way. Okay, so your positive s going to that way. Now, if the positive s going to this way here, now in order to form the directional derivative concept, so we cannot use the y-x coordinate system anymore. So what we have to do is we're going to have to look from this side here. Okay, look from this side here, and then if you look from that side, then you can see clearly. Basically, this is your positive s direction. This is still the y, right? Still the y here. This is a positive s direction, and this side here is a positive x-axis direction. So now this time the positive s and positive x-axis is different direction, right? Different direction. Okay. So you can help me now. Let's see if I'm going to redraw the curve at here. Which side is red? Which side is the green? Is this side red or green? It's green, right? So this side is green and here, and this side is red. Okay. Yeah. That makes sense? Okay. So now if you have initially at x equal to 1, for example, then you go to 0.99. See here, right? So because see, this is clearly shows you have a basically decreasing value for the function f because you got a negative slope at here. Right. So if I show you this curve right here, forget about the x-axis, y-axis, whatever. If I show you this and show you a slope line at here, you can immediately tell that this slope line representing what? A positive or negative number? Negative, right? Yeah. So this is the idea to have a proper orientation between the y-axis and the direction of a change, right? So when you orient these two properly, then you can clearly see whether you have a negative slope or positive slope. That makes sense? So maybe more precisely, what I'm trying to say is, from now on, you're going to have to get rid of the idea the slope is between y and x-axis. Now the slope is between what? Is between the vertical axis and the direction of a change, right? The displacement. Okay? Yeah. So this is what I want you to try to establish now. So now basically, slope is between vertical axis and the positive change direction, a positive displacement, So I use positive s, okay, s here. Okay, yeah. Now this is basically what we're going to focus on here, right? It's not really about the y and x axis anymore. It's about, okay, whenever you talk about slope now in 3D space, it's about the vertical axis change, right? This the change in the vertical axis, and the change in that positive displacement direction. Okay, yeah. So let me remind you a little bit another thing here. Now this is the simple example for function single variables here. Now what about let's see if I have a function of two variables, right? Function two variables. Then one thing that we learned previously, we have two special ones called two partial derivative. So this is a one partial derivative, and that partial derivative definition is given as this. Right, this is a partial derivative. Okay, yeah. So if this is a partial derivative, now you can think about relate this instead of basically calling this as partial derivative. You can relate this now to the so-called the directional derivative concept now. So if you look at this definition here, what direction is it going? Right? What's the positive displacement direction from this definition?
The positive x.
That's right. Right? The positive x-axis direction, or the positive I hat direction. Right? Yeah. So basically, you can interpret this partial derivative as the change or the rate of a change in f, okay, in the positive x-axis, right, or positive I hat direction. Okay? Yeah. That's basically what this partial derivative will give you. It's a derivative. What type of derivative is the derivative in the positive I hat direction? Okay. Now, similarly, you can consider what's the partial f over partial y, right, or partial f over partial z, that kind of thing. Okay. Yeah. So now the question here is we need to ask here is, okay, I sort of understand what the direction of derivative is now. Now, basically, what I really want is we want to derive something. We want to look at is arbitrary direction. Okay? Not a very a well-established direction, x-axis, y-axis, right? I want an arbitrary direction here, right, to find the direction of derivative. Okay, so arbitrary direction. Then what? Okay, yeah. So I'll illustrate this using function of two variables here. So let's see. Consider this function two variables. Okay, so I'm going to draw something in here now. Yes. Oh, sorry. Yeah. Is that good? Yeah. So basically now you can understand conventional derivative and a little bit unconventional derivative. Now we want a very general directional derivative concept. So you go into an arbitrary direction, and how can we interpret that? How can we obtain the formula to get a derivative value when you're going in that direction, right? Okay. Is that good now? Yeah. So I'll use this function two variables for illustration, because if I use function three variables, and then I wouldn't be able to sketch that, right? This is basically a surface, right? As we learned, whenever you have a function two variables, z equal to f of x, y, and that represents a surface. So I'm going to draw a surface at here. Okay. So let's say I'm going to irregular type of both type of surface at here. So this is your function z equal to f of x, y. Good. Now let's pick a point on the xy plane. Okay, so we're going to pick this point P naught. Let's say it's at initially at x naught, y naught location. Good. So this point, right? Apparently, if you go up from this point to the surface, then okay, the corresponding point on the surface is z naught equal to f of x naught plus y naught, right? Okay, yeah. Okay, so now basically the question here is from this point, initial point. So we're gonna basically change, okay, to an arbitrary direction. For example, let's say I'm gonna go to this direction in here. I'll use a unit vector here representing that direction. So it's like essentially what it means is going from here slightly to that direction by a little bit. Okay, yeah, that's basically called the direction. There's the change, right? Okay. So let's exaggerate a little bit. Basically, we can consider maybe a straight line passing through this P naught. Yeah. So let's just tend that a little bit, exaggerate a little bit. So you basically walk in that direction u hat, which is parallel to the line L. Okay. So always walk in that direction. Okay. Positive direction here. Is that good? Yeah. So at the same time, I want you to consider this. It's like you're walking a dog in a direction. Okay, so this is person A. Okay, gonna go in this direction at here, and then another person, okay, at here. Okay, that person on the top of here, B. Okay, and will basically move at the same time as this person A is moving, right? Okay, so if you move along this line L, so this person A will trace out straight line L, right? Then this B, and guess what? The B will not go anywhere. The B will always go along this surface at here. So basically, on the B at here, so the B will somehow, okay, I don't know, so somehow trace out a curve, okay, along this surface at here. That make sense? Yeah. Okay. So another question basically here is, if I you see that curve at here, right? See that curve? That's basically how the person B will move around this surface. So if you go from here to here in the positive u-hat direction, then the person B will apparently in this case will climb up, right? Okay, yeah. So now the question here if ask is, what will be the slope at this location, right? What will be the slope at this location? Or slope is always a concept. What will be the rate of a change? Right? What will be the rate of a change for this person B, okay, as it going to the next level, okay, next position? Is that good? Basically, is it going to climb a little faster or is it going to climb slower? That really depends on the surface, right? Depends on the surface. It's like this bee is climbing a mountain here. Okay, yeah, good. So then, to answer the question, right? Slope for the B at here, okay? Slope for the B equal to what? Okay? To answer that question, you essentially what you have to relate to now is to the concept I just mentioned. You have to think about the curve, reorient the curve between the vertical axis and which axis? The positive displacement axis, right? Yeah. So in this case here, the positive vertical axis, the vertical axis is basically the z-axis. Is that good? Right? That's a z-axis. And then the positive displacement is this direction here. So this is basically the positive s direction. Okay? The positive s. So I want you to think carefully. I want you to orient, right? Orient this vertical axis and the positive s in a way as the conventional rules. What's the conventional rule? The right-hand rule, right? Just the way as you orient the y-axis and the x-axis. So it has to be basically, it has to be z at here and s at here. This should be your orientation at here. That make sense? Okay. So now you tell me, which direction should you look at it in order to orient everything into this perspective? Should you look at it from this direction, or should you look at it from this direction? The second one, right? So only when you look at this direction here, it's like you have a plane, right? Basically, if you take that line here, you have a plane, and the plane cut this surface Z, generate this red color here. And then when you look at from this side of the plane at here, then you would be able to draw this curve, right, as Z and the positive S orientation. Okay, so basically you think about it. And now, if I'm going to draw a tangent lines at here, okay, draw the tangent line through that location B. That tangent line basically representing the slope, right? Representing the slope at that location. Okay, yeah. So you can, if you draw that thing out here, so it's like this is your B at here, right? This is your B. Okay. And that makes perfect sense because you see this slope is a positive slope, and that tells you exactly if when you walk in this direction, that person B will climb up, will have a positive slope at here. Yes. Looking from this side here? This side. It should be this side here. Yeah. Because if you look from this side, it doesn't give you the orientation ZS like this. Right? So whenever you orient the curve, you have to be oriented the positive here and positive S at here. Okay? Yeah. Come again? So, yeah, when you look from this side here, am I drawing okay? The slope is still point. No, so this slope is this way. Is that okay, right? Why on this side here? You mean? See, this is a positive S direction, right? You have to think about. You're going to have to stick on the other side, right? Like projecting. Yeah? Is that good? No? Okay, yeah, we can. But I think I'm over. Okay. Yeah, okay, I'll give you maybe 1 minute trying to project that in your mind here. Yeah. So it's let's say it's like this, right? Let's say this is a plane, right? When you're walking from here to here, this is basically the plane cuts through the L, isn't it, right? And then you have basically your curve goes something like this, and then you have your tangent lines like this. Then you look from this side here. Yeah, the left. Which is your left? Yeah, this is the left, right? Yeah. You look from the left, look from here, because you're going to the positive ZS direction this way here. Is that okay now? Oh, well, let's talk about it afterwards. How many of you still having trouble visualize this? Yeah. The bottom line is you have to think about the change, which is the vertical axis, with respect to the positive displacement direction, which is S at here. Okay? That's how you would orient this. And then the slope for this tangent line is this so-called directional derivative. Okay? Yeah. Or maybe use it the other direction. What about if you go to the other direction? Let's say if this is the other direction, right? And how would you plot this vertical axis and the positive S direction? Right. So if you this direction, then it'll be this orientation, all right, from this perspective. Okay. Yeah. Okay. So basically, the slope for curve. Let's see this curve right here, call it curve C. Okay, is directional derivative. Okay, yeah. It is a very much derivative related to very much to the direction. Okay, to the direction. Is that good? Yeah. And the other thing you can also visualize directional derivative is this. If you happen to have a ramp in front of your front yard, right, and you can go one way is this way, so that's one way of a change, right? Or you could go this way. That's another way of a change, isn't it, right? So apparently, when you're doing this, it will result in a completely two different type of slope, or completely two different type of change in the elevation. Okay, so that essentially is the idea of a directional derivative. Okay. Okay, so concept-wise, I think that's fine. But what we really want is we want a formula so that we can calculate this directional derivative. Okay, so let's formulate this one more mathematically so that we can come up with a formula here. So going along this direction here, u hat. So I'm going to basically, I'll let this u hat, okay, equal to a I hat b j hat. So that's a unit vector. So let's say certain direction, a hat plus b j hat. Okay. And this line L, okay, this is the line L at the trajectory here. Now for this line L, okay, I can come up with a line equation because basically the line L passes through this P naught with a parallel vector for u hat. So I can create the line equation. Now this time I'm going to use the displacement s as a parameter instead of the t as a parameter. So I'll say x of s equal to x naught plus s times a. Let me just use a times s, and y of s equal to y naught plus a times s. Okay, b times s. So this is your line L equation here, right? Okay, yeah. Okay, so directional derivative. So back to the simple. If you write derivative, that's single variable. You write df over dx, right? Okay. What's df over dx meaning? A change in the x variable and how much change in the function f, right? So that's basically df over dx. But now we are talking about is the directional derivative. Basically, a change in what? Not x. This time it's a change in positive s. So instead of a df over dx, so what we're looking for is what? Df over ds. Okay? Yeah. So that's basically what we're going to try to derive it here. What's the df over ds? So you have a small change in the s. What's the change in the function f? Good? Okay. So let's derive this directional derivative at here. Okay? Yeah. Before I derive, I'll write down the formal definition for directional derivative here. So the derivative of this function at this location in the direction given by u hat, okay, is denoted as this: df over ds, subscript u hat, okay, comma t naught, okay, like this. This is a little bit different notation than the regular derivative. So now you see here, because it involves direction, right? So we do put a direction u hat here to indicate what which direction is the directional derivative we're looking at. And of course, we also put down the exact point to calculate directional derivative if possible. Okay, yeah. An alternative notation you probably see in some other textbook, they write the directional derivative like this. Okay, yeah. So this will be an alternative notation. Capital D subscript u hat, function f, bracket, and then the subscript location p naught. I will, in my class, I will mostly use, actually probably I will only use this one here for the directional derivative notation. Okay? So, if I write down the formal definition, using the limit concept, okay, general directional derivative. So here's the directional derivative in the u hat at an arbitrary location. So then what do? We basically do this. You have initially at x location, okay, and the y location. Then you're going in the direction of u hat, right? And you will change a little bit in the u hat direction. So basically x will change by a multiplied by h, y will change by b plus h minus initial location, okay, and then you let h, okay, divided by h, let h approach 0. Okay. So that's the formal definition for directional derivative. Right. So h is a small change in u hat direction. very much like a single variable or a multivariable partial derivative concept, right? Yeah. Now, you can use this one to calculate derivative. Not a problem. You can actually do that. I think this is probably initially when you learn function single variables. How do you calculate derivative? You use a limit, right? You can use a limit to calculate derivative, and that's fine too. But this is not the very efficient way of calculating derivative. So I have an alternative formula right here. I'll give you that to you, and then I'll show you a small, quick proof at it here. Okay. So df over ds, okay, in the direction of u hat is equal to this. So let's call it alternative formula. Okay. Yeah. So I spent 40 minutes at it here talking about directional derivative. Now, when you look at the calculation of the directional derivative, it's not simple, right? What does it involve? The first term is the gradient. The second term is the direction. And then here is this dot product. That's it, right? So in terms of calculation of the directional derivative, you're doing is just a dot product. Okay, that's it. Okay, so I'll give you a quick proof for this one here. How this is true at here. Okay, so it's worth a little time to prove it. Okay, so this is what we're trying to get, df over ds. I'm going to use the chain rule at here. So partial f over partial x and dx over ds plus partial f over partial y and dy over ds. So both x and s, you can consider them as a function of the displacement. Okay, so when x can be a function of displacement, y can be a function of displacement. And as a matter of fact, they are, right? So you see our line L here, this is basically your chain. The x and y will change along this line L. They are a function of s at here. So we can rewrite this dx over ds, and that basically equal to a at here. And this is b at here. Okay? So the derivative of x over s is a, and derivative of y over s is the b. Okay? And this term, we can rewrite it into a dot product between two vectors. And this is essentially gradient dot u hat. Okay? So that simple proof for this directional derivative. Is that cool? Yeah. That's it. So if you need to calculate directional derivative, all you need to do is calculate the gradient first and then dot the direction. Okay. So let's take a look at the example. Okay, we'll get better interpretation or gains in-depth insight into this formula shortly here. Okay, so let's take a look at an example. Here is a function of two variables here, and we wanted to calculate the df over ds, okay, at 2, 0 point in u hat. Let's see, not u hat, in direction v equal to 3i hat minus 4g hat. So let's say we want to calculate this one here. There's only one little twist at it here. Okay. Formula. We got our formula here. So here's our formula. So first thing we need to calculate del f. So this is a function calculating del f, partial x, partial y. very simple partial derivative. First one here, e to the power y minus sine xy, and then partial x times y. Second one in here, partial f of partial y, you get x e to the power y, so that's not changing. And the second one here, so x sine xy. Here's your gradient, del f. Yep. Okay, so we're looking for this directional derivative at the 2, 0 point. And you can calculate this gradient at a 2, 0 point. So basically substitute x equal to 2, y equal to 0 into this vector. That's 1 and here, minus a 0. X is 2, 2 times 1, minus 2 times 0, so that's 1, 2, right? So this gradient at this location is 1, 2. Okay, and now if I look at this formula, if I need a calculation of the directional derivative, I need this dot, the u hat, okay, the u hat. But for this question, what it gives, it's not a u hat. It's what gives just a vector. You need that you're going in a direction given by the vector there, right? So basically, we need to normalize that vector to get the u hat first. So normalization gives us 3, 5 minus 4 over 5 like this. That's u hat. Okay. Finally, you get your df over ds in the u hat, and the p naught. The u hat direction at the p naught location is 1, 2, dot 3, 5, negative 4 over 5 like this. Okay, so that's 3 over 5 minus 8 over 5, which is negative 1. Okay. That's the directional derivative. So in that direction, you get a directional derivative which is equal to negative 1. Okay. Okay, so next one, I don't want you to calculate, okay? I just want you to stare on it and answer it as quick as possible. If we have a function f, so let's say z equal to f of xy, and then I'm asking you, what does this equal to? Yes, very good. Right, so this is basically the symbol here means directional derivative in the I hat direction, and you can verify. Right, that's the idea, and you get partial f over partial x. Okay. Yeah. Good. Okay, so that's all about directional derivatives. In terms of computation, it's very simple as that. Okay, yeah. But there's a very good application for partial derivative, okay, and which will come to that. All right. So now let's continue in here. Now we'll have a little bit in-depth insight into this into the directional derivative. Okay, so let's start from the formula and here. this is a partial derivative formula. It's a dot product between two vectors, basically. And now I'm going to rewrite this one just slightly, because whenever you have a dot product between two vectors, you can use the formula for dot product, which is what? Okay, that's another formula for dot product, isn't it, right? Okay, so based on this one here, the u hat is a unit vector. Then the absolute value for the u hat must be what? 1, right? So that term is gone, and all you're left with this. So it's like here's your del f, and here's a u hat, here's a theta. Okay. Yeah. Is that cool? Okay. So now based on this one here, now I can summarize this prop into 3 different properties at here. Okay, 3 different properties. The first property, okay, if you look at this formula here, this is a directional derivative, and equal to this times cosine theta. Okay. Now basically, when theta equal to what value that this expression will reach maximum? 0. So this is 0 degree. When this is 0 degree, then df over ds is maximum. Okay. And then you can answer the question here. What's the value of the maximum? The maximum value here equal to what? Equal to this. And what does 0 degree mean? 0 degree means what? Yeah, so come again. No projection, just 0 degree basically means these 2 vectors become the same, right? So basically the u hat, remember what u hat is, right? U hat is the direction of the change, right? So it's the direction how you're walking to. So now when 0 degree basically means you're walking in which direction? Which direction? The direction given by when it's 0 degree, you're walking to the direction given by what? By del f. Okay? Yeah. Now you got to basically another thing you got to bear in mind is when you are giving a function f of x, y, then its gradient you can't change anymore. At this location you have a gradient pointing in the right direction. That you can't change anymore, right? Yeah. But from this location you can certainly choose which direction to walk to. Okay? But if you walk in the direction by this del f, then you get the maximum directional derivative. Okay? So now can you think about this, the meaning behind this one here? So what does that mean? So when you're walking in the direction given by the del f, you get a maximum directional derivative. So coming back to this graphite here. You're walking, let's say, in the direction given by del f. You get a maximum directional derivative. What does that mean for this person B at here? The person B will have the fastest rate of change, right? So we'll basically climb at the fastest rate of change. Does that make sense? Okay? Yeah. That basically is the first property here. And the second property is the negative. If theta is pi degree, 180, so basically this time okay, the u hat is in the opposite direction of the del f. And then everything will basically will flip, right, from this property number 1. So the df over ds and the u hat is minimum. Okay. And the minimum value is equal to negative this. Okay. And then u hat is in opposite direction as del f. Okay. So the second one is just a natural deduction from the first one. Then you can basically interpreting if you walk in the negative direction of this as the del f, then a person B, instead of climb as fast as possible, now the person B will what? Will drop as fast as possible, right? Yeah. Yeah. Okay, so last one, the third property. Then what happened? Then the other one is what about you can take a guess what value what am I going to take now? 90 degrees. Okay, so pi over 2. So if this is a pi over 2, meaning this u hat is perpendicular to the del f. So if you look at this formula, cosine pi over 2 is how much? 0. So if this is 0, then basically means the directional derivative equal to 0. So then we get df over ds equal to 0. Okay? Yeah. What does 0 mean? No rate of change. So basically, when you're walking in the u hat direction and happen to be perpendicular to this del f, no rate of change, which means that person B, instead of climbing up or going down, that person B is doing what? You're circling, right? It's basically walking along the hill without a change here. Okay? Yeah. And I want you to relate to the concept we learned previously. When you are walking along this surface without change, what do we call that curve? Level curve, exactly, right? It's not a circle, it's not necessarily a circle, right? It's a level curve, basically. Okay? Yeah. So no change in f, okay, in such direction. So basically, it's a level curve. Okay, those are very important to actually concept we'll make use of in the next lecture when we learn how to get the minimum or maximum value for a certain surface. Okay? Yeah. Yes.
Does that mean that the line L matches to the level curve at point B?
My line, yes. Yeah. So basically, the u hat will be tangent to the level curve. Yeah, the direction of walking. Very good. Yeah. So I'll give you a simple example right here, right? Let's see. I use this quite a lot. We have this z equal to x squared plus y squared, for example. Okay. Yeah. This is a paraboloid, right? We draw it before. Okay? Right. And I illustrate you this one here quite a lot. Basically, if you slice this surface, use a cluster of planes, okay? Then you basically get a whole bunch of circles, right? A whole bunch of circles. And then when you project all the circles into the xy plane, so you get a cluster of circles centered around the origin, isn't it, right? Okay. So in this case here, if you are going to draw the grading vector, remember the proper way of drawing grading vector. First, calculate the grading vector, and then like you draw the vector as you draw the vector from origin. but then you need to move the vector to the location, right, where you calculate it. So in this case here, we're going to draw this vector basically at this location. That gradient vector will pointing out to this direction. And gradient vector has a couple properties. One of the properties is what? The gradient vector is perpendicular to what? To the level curve, right? To the level curve. So I'll look from the top here just to make your life a little bit easier. So if looking from the top right here, if this is a level curve, if this is the location, I'm just going to draw the gradient vector. So that's perpendicular, right? Yeah. Is that good? Yeah. So now you think about it. If you are going to, at this location, let's say this is 1, 1 location. Okay? If this is 1, 1 location. Now we're going to ask a question here, basically 3 different questions. Okay? Question number 1, can you give the direction of max rate of a change or rate of increase at 1, 1? And can you give the direction of the minimum rate of increase, or I wouldn't say, yeah, rate of increase at 1, 1. And third of all, can you give the direction, okay, direction of 0 rate of a change at 1, 1. So before you start to solve this, and this is a very simple here, you know, we graph this already, right? We graph this, and honestly, you don't have to solve, but then you can actually try to illustrate to yourself even before you do the series calculation in here by answering the question 1, 2, 3. Okay. So for example, the first question: what's the direction from this location 1, 1 that you can have the maximum rate of a change for the function f? Which direction? Or this is 1, 1 here, right? The direction, which direction you should let x, y change so that you have a maximum rate of a change? Del f, right? So basically, the first one here is this direction here. Okay? Yeah. A second one here, I guess, negative del f, right? Yeah. The last one, right? The last one here. So this is the location here. Which direction do you change the x, y such that there's no change in the function f? Excellent. So tangent to the level curve. So basically I say, okay, I probably will go this direction here, right? Any other choice? Exactly. And the opposite, this one here. So basically the last one here will have 2 solutions, isn't it, right? Yeah. You can either that direction or that direction. You will have 0 change in the function f. Okay? Yeah. So now, once you get this clear, and I think you can get down to the series calculation, that should be very easy. Yes? Could be, but in this case, just this one single condition is not enough. Yeah. But you can clearly see, right? So if you walk this direction, even though this direction of the river is 0, but this is definitely not what? Not the local minimum or local maximum, isn't it, right? Yeah. So that's a very, very good question. So you had to basically, later when we learn this local minimum, local maximum location, we will use this condition, the direction of the river to be 0, right? But that's not the only condition. Yeah. Very good. Okay, so let's solve this one here, just to get some idea of this thing here. Okay, yeah. We actually solve already. The first one says we always said we understand ourselves. The direction for the maximum rate change is given by the del f. But if this asking is a direction, then basically what we need to do is we need to basically normalize this del f to give us a unit vector. So that will be a direction here. Okay, that will be a direction. Del f can be calculated easily. For this function is 2x, 2y. Then at this p0 location, you get 2, 2 at here. So that u hat for the part A, the u hat is basically what? Because u hat essentially is equal to 1 over root 5 to 2. Okay, yeah. And the second part of the question is negative u hat or equal to negative root 1 over root 5 and 2, 2. Good. Okay. Last part question. Third. So last part is you need a direction u. Yes. That's the length of the grading vector. Oh, sorry. Length is not root 5, right? Of course not. What is it? 4 plus 4, 8. So that's 2 divided by 2, right? So you can simplify this a little bit, yeah? Yeah. Good. Thank you. Good. So the last part question, okay? We need the u hat to be perpendicular to this del f. So this is essentially the part we don't know what the u hat is. We only know it's perpendicular to the del f. So okay. In this case here, instead of u hat, I'll call it a u first. Okay. So let u equal to a certain vector ab. If I can find a vector u that is perpendicular to this del f, then I'll normalize this u to give me the u hat. Is that good? Yeah. Okay. So this dot that equal to 0. And del f is 2, 2. So basically get 2a plus 2b equal to 0. Okay. So 2a plus 2b equal to 0. So what's a and b? Zero? No, zero is not a vector. You need a non-zero vector, right? Can you give me an option? 1 minus 1. Good. So I can have ab equal to 1 minus 1. What others? Is there any other options you can have? ab equal to negative 1, 1. Very good. Right? Okay. So now you can derive, then what's the u hat? The first u hat, let's see the first one here. Normalize this, which is the second one here. So that's one way of solving for the perpendicular direction. Okay, perpendicular direction. There's another way. Okay, this one here, I probably can call it sort of a observation type of approach. And another approach you can do is this. Okay, so let's say the other approach, what you do is you directly work on this u hat. Let's say you let the u hat equal to CD. And you know your u hat is perpendicular to del f, so that's why CD dot 2, 2 equal to 0, which gives 2c plus 2d equal to 0. Okay? One equation now. But in order to solve for two variables, you need a what? Another equation, right? So what will be the other equation? The u hat is a unit vector, so which means, okay, yeah, this square root for c squared plus d squared equal to 0. So now you have two equations, two unknowns, then you can solve for the c and d. Okay, the solution of c and d will be the same as this one here. Is that good? So either way is fine. The first one, I typically use this one here because it's for simple vectors, it's straightforward. Right, it's easier just to look at it, then you'll be able to get it. Okay. Yeah. So this is basically the directional derivative and the two properties added here. Okay. Yeah. So let me give you another example here. Okay, it's a little bit of variations in terms of directional derivative. Okay, it's a little bit long writing it here. Let's see if we can solve this one here. We have a function of 3 variables here, and it says this function, the derivative of this function at a certain point p, okay, will be the greatest in this direction, and that directional derivative in that direction is 2√3. Then the question here is, what's the gradient of del f at that point p? Okay. Yeah. So think about it first. No, actually something just struck me first before we solve this one. Now remember in the previous lecture I mentioned about one thing. I want you to remember at least one thing from this lecture is the meaning of a grading vector, right? So basically, which is what? The grading vector represents the direction of the greatest change in function f, right? And I said I didn't provide you the proof, but I can provide you proof after the directional derivative, okay? Yeah. Now the proof is actually we already talked about it when we're talking about the properties that are here. Sorry, the properties here, right? The properties here. Okay. So if you look at this first property here, when you are walking in a direction given by the del f, the directional derivative is the maximum, and the maximum is what? It's this, right? It's this. So basically, that's a statement we just said. If you go in a direction given by del f, you will have the maximum rate of change for the function f. Okay. Yeah. Okay. Coming back to this question here. Okay. Coming back. It's actually not difficult. It's just a change, a perspective in terms of solving this one here. Okay. Yeah. Your best bet is still the formula. What's the formula here? The formula is directional derivative in the direction given by v equal to the gradient dot v hat. That's your formula. Now, the question didn't give you the v hat; it just gave you a v, but that's okay. Okay, yeah. So we can always get the v hat. it says the derivative of this point is the greatest in this direction, right? It's in this direction. But then the question here is back to the property. If you have a point here, forget about any direction, a vector here. If you're given a point, which direction will give you the maximum rate of change? Del f, right? So basically means the direction given by the v will be what? The same direction as given by the del f. Okay, so del f and the v will be the same direction. So I can literally say that the del f is basically a multiple of this direction v hat, right? Yeah. And v hat, I can normalize that to give me this one. Okay, so this is your del f, the same direction as v hat, or v hat is the same direction as del f. So plug it back into this this formula right here. Plug it back into this formula. So df over ds in the v hat direction. First of all, the question told you already. The directional derivative in that direction is 2 root 3. And that equal to del f, which is k v hat dot v hat, right? Dot v hat. So we already got v hat. The only thing we don't have is the k at here. So v hat dot v hat actually is how much? 1. So basically this is k. So the k equal to 2 root 3. Then 2 root 3 times this one here, then you get your del f, which is 2 times that. So 2i hat, 2g hat minus 2k hat. Okay? Yeah. That's it. So that's this question. Yeah. Okay, so I have a little bit in terms of the directional derivative estimate of change, and then we'll get into the meaning the maps. Okay? Yeah. Any questions? All good? Okay, thank you.